centimeter cubic box with its edges aligned in the XYZ axis, and it's in an electric field which depends on the x coordinate and points in the y direction. The units of our electric field are newtons per coulomb. Our x in here is in meters. What is the net electric flux through the box, and what is the charge of the box? So first thing we'll do is let's draw the box. Try my best at drawing three-dimensionally here. So there's our box. And it says the edges are aligned in the XYZ axis. Let's say that the corner of the box is right at the origin. So there's our x-axis. There's our y-axis. And our z-axis then comes out of the page. X, Y, and Z. We want to find the net electric flux through the box, so let's write down how we calculate electric flux. So electric flux is the integral of E dot dA. So what we'll have to do here is for each of the faces of the box, let's do the integral of E dot dA. Once we get each face done, we'll add them up and we'll find the total flux through the box. So let's start with the flux through the right-hand face of the box. So let's start with the flux on this side right here. So the right-hand side, right face. So on the right face, that's this face right here it has a constant x value, which is the same as the length of the box. So every edge is 1 centimeter long. So every edge is 1 centimeter. This guy too is also 1 centimeter. So for this face of the box right here, the x value is 0.01 meters. Which means that the electric field is 350 times x in meters plus 130, and that's in the j hat direction. So 350 times 0.01 is 3.5. 3.5 times 130 is 133.5 in the j direction. There's our electric field. What we notice about this electric field is that it's constant. So we want to put our electric field in to calculate our flux. Net electric flux is the integral of E dot dA. Electric field is constant, so it comes out front. E dot the integral of dA. Integral of dA is just A, is E dot A. Okay, so we know what to put in for our E. What do we put in for A? So A is the area vector of this face of the box. The magnitude of the area vector is 0.01 length times 0.01 width times the direction. So the direction of this area vector is straight out of the face. There's the area vector of the front face of the box. It's aligned with the x direction. So that direction is I. So let's fill in this area with this electric field and we'll calculate our electric flux. So our net electric flux is 133.5 J dotted with 1 times 10 to the minus 4I. J dot I is 0. So two perpendicular vectors, when you take the dot product, it's 0. So the net electric flux through the right face is 0. That makes sense. The electric field vectors point up, so none of those vectors cut through that face of the box. Next, let's do the left face of the box. You probably know where this is going to go. So the left face, on the left face, the x coordinate is 0. So everywhere here on this left-hand face of the box, x equals 0. So our electric field vector is 350 times 0 plus 130, points up in the y direction, so 130 j hat, also constant. So our net electric flux is E dot dA equals E dotted with the integral of dA equals E dot A. What is the area vector? Area vector on the left face of the box points out of the box. That's in the negative I direction. So A is length by width again. But on the left face of the box, the area vector points towards the left, so the direction is minus I. Oops. So then our electric field is, or our electric flux is 130J dotted with 1 times 10 to the minus 4 negative I equals 0. Because again, J dot I equals 0. Okay, there's our left and right face. Next we'll do the top and bottom faces.